Hello and welcome back. In the past few videos we talked about rotary embeddings and activation quantization. In this video we're going to talk about sparse sliding window attention. So let's get into it. So to start off, you'll notice that we have this initialization code for self.compressor and self.indexer. What are those? Let's build some intuition. So traditionally with attention, when you're predicting a particular token, you want to attend over the KV entries of all the tokens before you. And one problem with this is that when your sequence length gets really long, there's a lot of memory and compute. So what DeepSeek V4 proposes is a combination of sliding window attention and compressed memory attention. So what is sliding window attention? The basic idea is that instead of storing all the past KV entries, you're going to store a sliding window, maybe the last K elements. And so if you're trying to predict, for example, the token here, you're going to attend to these last 5 tokens. Now, as you can guess, this is problematic because what if the token here is really important? Then you've lost that information. And that is where this compressed memory KV stuff comes in. The idea of the compressed memory KV stuff is that you have all these KV entries at the granularity of tokens. And what you do is you compress them into more coarse compressed key value entries. So for example, this entry right here will compress 8 of the most granular KV entries into a single coarser entry. And then what you're going to do is whenever you need to do attention, you have this lightning indexer, which knows for a particular query how to attend to these more coarse compressed key value entries. And then the combination of this compressed memory attention and this sliding window attention gives you kind of the best of both worlds, where for recent tokens you have very high fidelity, and for the rest you have this compression thing that allows you to at least see the whole sequence. So going back to here, you can see that the compressor and indexer, they're just initializing. And one thing you'll note is that this compressor is basically indexing a view into the KV cache starting at the win position. And the reason you're doing that is because the first win elements are reserved for the sliding window KV cache, and then the rest is reserved for this compressed memory KV. Okay, so after we initialize the compressor and indexer, we now come down to here. What is this doing? This is morally just giving you the last K indexes. But the reason why you need a fancy function to do it is because this sliding window KV is actually going to be a circular buffer. So for example, if you have 0, 1, 2, 3, and you want to add 4, you actually replace 0 and you put 4, and you do the bookkeeping to know that the actual order is 1, 2, 3, 4. But at this point, we want to have the actual 1, 2, 3, 4, and so this does the logic to look into the circular buffer and give you the tensor that actually corresponds to the right order. Okay, and then what does this do? So what this is doing is it's telling it, if you have an indexer, then it's basically doing the logic we talked about here, where it's going to give you index scores that you can use to weight the relative compressed key value entries. And if you do not have an indexer, you're going to just use a heuristic to calculate it. And then you're going to concatenate the sliding window, but also your compressed IDXs to get your top K IDXs. Okay, and then now we come down to here and we see that it's split into 2. If start position equals 0, this basically means prefill, else we're going to do decode. So let's talk about prefill. So if the sequence length is less than your sliding window max length, then it's super easy. You just put your KV into your KV cache. However, if it's longer, then you have to do kind of the indexing thing we were talking about earlier, because you might have this overlapping thing. Once you fill your sliding window KV cache, then we do the compressor KV cache. And once we do the compressor KV cache, we concatenate KV, which is your original KV, and then also your KV compress. Now, astute readers will notice here that this KV might actually be longer than the sequence length. And indeed, that's true. And so what this implies is that first prediction, when you're pre-filling, is actually going to be more accurate than subsequent decodes, because subsequent decodes are going to be limited by this sliding window length attention. And then we call sparse attention. And for decode, it's a lot simpler. We basically just insert our calculated KV into the KV cache. We call the compressor. And you'll notice that this is actually going to mutate the internal state when we call self-compressor extraposition. And then we call sparse attention. In a future video, we might go more into the details of the sparse attention kernel, but hopefully you kind of have a high-level intuition as to like why DeepSeek did it this way and the merits behind having a combination of sliding window and compressed summary attention. So yeah, hopefully that was interesting, and I'll see you in the next one.